Okay, to complete your instruction on numbers in different bases, we're going to talk about converting numbers from one base to another. First thing we're going to do is review how place value works in different number bases, in case you've forgotten that since the last video. Then we're going to look at converting numbers between different bases, in particular between base 10 and other bases. And finally, we're going to give us an explanation of what this has to do with the cryptography side of our class. It's in particular how it connects with computers. All right, so let's pretend that k is a number that is at least 2, and so we're looking at numbers that are base k. If we're looking at a number in base k, if we want the digits, what the digits of those numbers are, basically we start at 0, and then we end at k minus 1. Now, there may be some issues if k is bigger than 10. If that's the case, we use some other symbols for digits. The one we're going to use in our class and the one that is used in most applications is the letters of the alphabet in alphabetical order starting with A. And the idea is once a digit goes past 1, when you're counting, you cycle back to 0, and then you increase the digit to the left of that by 1. All right, so let's look at an example. Again, this is kind of review. We did something very similar in the last video, but I just want to let you get an idea of looking at different bases. Now we're looking at a number in base 8. So we get 2, 4, 7, 3, 6 in base 8. We're going to convert that to base 10. Now, I can't emphasize enough that that number is not 24,736 as we see it. This is a number written in base 8. So those places are not powers of 10, like we think of it. The ones place, the tens place, the hundreds place, the thousands place, etc. These place values are powers of 8. So if we're looking at the place values of this number, if we're looking at that 6 is still ones. A 1 is a 1 no matter what base that you're in. And that tells us that we get the number 6 times 1 equals 6 from that. And that's our ones place. But our next place is not going to be the tens place. Remember, we're in base 8. So that 3 represents 3 copies of 8. So we get 3 times 8 is 24, rather than 3 times 10, which would be 30 in base 10. So if we're looking at the next place value, then we go to the next power of 8, that's 8 squared, and we get 7 8 squareds. So we multiply 7 times 8 squared, we get 448. The next one is the 8 cubes place. We got 4 of those, and so we get 4 times 8 cubed. That gives us 2,048. And then finally, our last one is the number 2. That's in the 8 to the 4th place. And so we get 2 times 8 to the 4th equals 8,192. And now we just add up all those numbers to get our representation in base 10, and we get 10,718. Notice that the digits on our base 10 are a lot smaller than the digits we get on the ones in base 8. That is because it takes us longer to cycle through to 0 in base 10 than it does in base 8. So our numbers look, they're not literally smaller. These are literally the same number, but they look smaller if you're just looking at their digits. All right, so now we're going to go backwards. We're going to take the number 35,278. That is in base 10. And we're going to convert that to base 16. And as we'll see, I'll give you the fancy terms at the very end of this video. But base 16 is a special one. That one's called hexadecimal. Now, hexa is the 6 that comes after that. And the decimal is the 10. So you get 10 plus 6 is 16. All right, so how do we figure out what the place value numbers are going to be for this hexadecimal number? Well, there's a couple ways you can do it. There's one way where you can do it lowest place value to highest place value, but I'm actually going to teach you how to do the highest place value to lowest place value. It's actually very similar. So I'm going to look at how far to the left I'm going to go for these numbers. And again, these are in base 16, so I'm looking at powers of 16. So if I look at various powers of 16, right, I might get to 16 cubed, right, and get 4,096, and note that that is smaller than 35,278. And then go to 16 to the 4th, and notice that I get a number bigger than 35,278, well north of 60,000. So that tells me that my highest place value is going to be the 16 thirds place, right? 16 to the, I'm sorry, not 16 thirds, 16 to the thirds place. Woof, I'm having a hard time here. All right, so first question that I'm going to ask is, okay, so I know that 16 to the third is going to be my highest place value. what number am I going to put in there? In other words, how many 16 to the thirds are in 35,278? Well, one way of thinking of that is asking myself, okay, well, how many multiples of 16 to the third do I get without going over 35,278? And if that sounds like a familiar problem that we've been working on in this class, but you're right. We're talking about quotient remainder. We're talking about dividing 16 to the third into 35,278 and seeing what the quotient is. That's going to be our place value. And then what the remainder is to figure out what our other place values are. So when we do that, we get 35,278 is equal to, 16 to the third goes in 8 times. So you get 8 times 16 to the third. And then our remainder is 2,510. So that tells us that in the 16 to the third spot, we're going to put an 8 there. Okay, so how do we figure out the other place values? Well, we're going to look at the remainder, right? The 8 16 to the thirds takes care of everything except for that 2,510. So we're going to look at 2,510 for how many 16 squareds are going to be in there. And we're going to do it in the exact same way. We're going to do quotient remainder, dividing 16 squared into 2,510. And it turns out we got 9 of those that go into there with a remainder of 206, which tells us that we get 9 16 squareds. So far it's going pretty well. And now we take the to see how many 16s we have. That's our next place value. We're going to see how many ways 16 goes in, how many times 16 goes into 206. And this one is interesting because when we do this one, we get a quotient of 12, right? So we want to put 12 as our next place value, but 12 has 2 digits. So we can't literally put 12 there. So what do we do? What do we do with that 12? Well, remember, we're in a number system that has more than 10 digits. We have 16 digits. So what we're going to do is, well, we have to do something. We need a different symbol for our 16 fingers. So we use the same 10 digits as we use for base 10, but that only takes care of 10 of our fingers. For the remaining 6 fingers, we have to use the letters of the alphabet. So we start with A, which represents the number 10. And when I write that 10, that's 10 in base 10 with our 10 fingers, right? B represents the number 11, C represents the number 12, D represents the number 13, E represents the number 14, and our 6th additional finger is F, which takes us up to 15. Now, remember, we were dividing 16 into 206 and got a quotient of 12, so 12 corresponds to the letter C, so that means we get C in the 16s place. And then finally, we look at our last remainder, which is 14. 14 is represented by the number E, which tells us that E goes in the 1 spot. So to summarize what we've done here, we found that we had 8 16 to the thirds, we had 9 16 squareds, we had C 16s, again C represents the number 12, and then finally we had E 1s, E represents the number 14. And that means our hexadecimal representation of the number 35,278 is 89CE, and we can either write that with the written out in letters version of the number 16, or if you want to write it as 89CE and hexadecimal in parentheses, that's a perfectly reasonable way to do it as well. All right, so now I want to sort of talk about some of the important bases that we are going to be looking at. In particular, how bases are important for computers, which is kind of the next set of ciphers that we're going to be looking at, computational-based ciphers. So if we're using a computer for any kind of encryption or decryption, the thing about computers is they can really only deal with 2 states, 2 digits, and those digits are 0 and 1. Fortunately, 0 and 1 are perfect for writing numbers in base 2. And the special name we give to numbers written in base 2 is binary. So binary representations are representations in numbers in base 2. So that's if we had 2 fingers, 1 on each hand. However, so that's great for computers. Computers love base 2 because we can write base 2 numbers and they can understand it well. However, from a human perspective, base 2 is pretty horrid. And here's, well, horrid is maybe a bad way to say it, but it can be inconvenient. And let me show you how. So if we're looking at the number 92, that's nice compact 2 digits way of representing that number in base 10. If we were to represent that in base 2, that would be a pretty big number. We go from 2 digits to 1, 2, 3, 4, 5, 6, 7 digits, which is pretty inconvenient. And you can imagine, even with relatively small numbers like 3-digit numbers in base 10, you get huge number of digits in base 2. So we want nice ways of representing base 2 numbers in bases that are larger, so that we have smaller numbers of digits. Right? So we could think, well, why not represent them in base 10? Well, as you've seen, representing numbers in base 10 can be kind of inconvenient. It turns out there are certain bases that are much more convenient for base 2, and you'll see some of those in the activities that you're going to be working on. One of those is base 8, and that has a special name. That one's called octal. And one of the other ones that is really convenient is actually base 16, and that as we've seen, this one's called hexadecimal. So base 8 and base 16 are the two most important bases outside of base 2 and base 10 for working with computers. And the reason that's going to be the case, and again, you're going to see this in the activities, is that 8 and 16 are both powers of 2. And actually, it turns out base 4 is a nice one too, our Lobster World one, because that's 2 to the 2. But we usually like to go to, or people working with computers usually like to go to a higher one than 4. 4 is still too low. So 8 and 16 are nice powers of 2 that people can use. So what happens is the conversion is easier from base 2 to those bases than other bases, particularly base 10. All right, so now I think you're ready to look at converting between bases. That's the file that is included with this video.